we do. Oops.
Go back to the presentation.
I thought that this presentation would be this afternoon, so we didn't prepare anything. Just before, told my students I should push.
Presentation, please get the presentation back up, or is it up here? Ah, thank you.
Sorry about it.
AI is easy, by the way. It's AD that's hard.
I hope they.
This is good. Over
Yeah,
here.
you're always good, but oh, okay. It's working there. Okay. Our team consists of 3 groups. One is major. The Hubo lab is doing all the tasks and the control and vision design and everything. And Rainbow Company, that is part of Hubo lab. My institute, Kaist allows us to operate very little enterprise named Rainbow. So this is kind of Kaist-owned small enterprise. So they have some professional staffs and machining guys and some electronic technicians. So they made the whole Hubo robot in Rainbow. And our team, vision teams, we invited vision team in Kaist. They deal with mostly LiDAR data processing and vision data processing. The workload is, Hubo Labs work is about 45%, and Rainbow covers about 40%, and the vision covers about 10 to 15%. That is the workload. When I started this project, what is the most important point to cover? We have very limited source of communication, so the autonomy and supervisory balance must be very, very important. So we take care of many efforts to get the good balance between the autonomy and supervisory. And also, we have to optimize the way to use of low bandwidth and burst signal. So we have to make use of both signal at a very effective way. And third thing is that we found that the main robot struggled with the moving around, mobility. So we have to think of how to improve mobility. And another advantage of ours is that we have Rainbow Company, so they could make everything by ourselves. So if we have some problems, we can fix it immediately. That accelerates the development. And also we design a customized motor driver. That is very versatile, so it can do the push and control, control, overload, and plus we call non-symmetric the switching capability inside. So it allows us to drive the motor as a torque source. So that is very useful for egress task and also interact with the environment with flexibility. When I started this project, usually what he did thus far is that the robot stayed there, robot is moving around, and he's doing everything by himself, no interactions. So turning valve, or driving a car, we need very strong interaction, and distance will be changed, and opening door. If we do not have a very effective compliance, all the mission will fail. But usually, if we put the closed loop sensor there, This our feedback loop, the non-colloquial feedback loop introduced some instability with high gain. So we had to have very compliant control systems. That custom design motor driver helped a lot. And also we designed our own operating system in Hubo. Hubo is Korean word, is grapefruit, and the grapefruit composed of many grains. So we a small procedure we call R. R means each grain of grape. So it composed of many R's. So each student or group design own R, put R, and add it in independently, and as a whole, it worked as one system. So it is very easy to make many programming in different way, but combined into one system as a whole. And we found that other thing is that we should have very stable power system, power management system, because the motor, each motor drives, the current level is very dynamic. Dynamic range is very high. Sometimes 30 amps, sometimes 0, and sometimes it draws back. Back EMF drives the other way. So it deteriorates main computer and many processors. If that kills the main computer and communication units and etc., then it will be a catastrophe. So we are very careful to design a power distribution system. We put support caps and many relays to and the power management chip, always monitoring the power level, and in many cases they adjust the power level. Another thing is the heat dissipation. The less time the shaft use hydraulic cooling system is very powerful heat dissipation system. So we tried different kinds of heat dissipation system. Finally, we choose air-cooled system. We have fan and fin with the effective area. Then it was very effective to remove heat. So by adapting those things, we can overdrive the motor in 3 or 4 times in the specification. And last one is that very effective and intensive practice and keyboard. This is Hubo, nothing very special. It's just usual humanoid robot. It is not designed for the disaster response. Because the mission, the gear suggests to us, is that just drive a car, egress from the car, open the door, and turn it back, and make a hole, and remove debris, and walking over the rough terrain, and climb up the stairs. This is very usual. It's not a disaster situation. So we thought that you don't need to have very special robot. It just is strong and the normal size robot with very stable walking is enough to be the disaster response robot at this moment. And the vision system, most of them are using very complicated standard LiDAR and camera system. But when I started, I thought that in human robot is just move like this way, so continuous gathering of LiDAR may not be quite effective. So we decide that just scan the LiDAR when you need it to get the information from the world. And this camera is monitoring and where to see. So we simplify the vision system very effectively. And this is power management system. In upper side, we have very strong support cap. So it can run at least 30 minutes without any external power. So if the main power goes down seriously, still main things is the computers and communications and gyros, they will be surviving for a moment. This shows cooling system, air cooling system on the knee, usually on the knee and ankle. and you saw the wheel. I showed you how to transform the wheel. And another thing is that there's small pore there, small pore and some LED there. That is usual optical mouse. So we modify optical mouse, and when it rolls on the ground, it can automatically, so it can detect the sleep and the direction. So rate gyro, and then automatically guess the distance and everything. And the business, we tried full automatic driving by himself. But the thing is that our LiDAR is fixed, so we can move like this way, and it is too slow to get all the information. So we decided to fix the angle, and during the running, it reconstruct the environment. It is not exact slam, and we find a way how to get through. So we use that kind of things. There's an experiment. We did gazebo simulation first, and then this is gazebo simulation. Actual experiment was done like this way. This is actual field. Another unique thing is that before driving a car, we have to think of how to get out from vehicle. So we have developed very interesting tools that, as you see, that we sit on side and we accelerate out with cable. So it's a very simple mechanism. So the gear allows us to use that mechanism. So it is possible we put the robot inside. And we have a very strong wrist with the slip ring, so we can rotate unlimitedly. So we can handle the steering wheel very fast and very quickly. Egress test. When I designed egress test, I tried many egress with car. What I found is that most of the car, we cannot ingress or egress statically. We usually jump in and jump out. So that's the reason that old man needs help, because statically is impossible always. At last moment we have to jump. So I found that the static movement of egress is very, very difficult and also impossible. So I decided to use dynamic egress like human. To do that, we have to jump in some sense, and without losing stability. So we use supporting arm like this way. But the thing is that, as you see that when you hold this the bar like this way, if you do not have very good pushing control, then you will run all the motors, because this is power, internal powers, and if the pushing is a little bit squeezed, then the power is not so strong to hold all the 180 pounds of robots, so it will burn and break everything. So at the first experiment, we break many four-stroke sensor gears and fingers and many things. But so we have to apply very effective compliance control. I'm not sure they okay. This video all of you are not working. We need more powerful PC. I just went first we have a so-called there are many ways to make zero gravity control, so we can control the so-called okay, so I want all talk method make it possible make the geographic motion. But in that case, it is very, very hard to eliminate frictions because we use very high reduction gear ratio, more than 250. It's not back drivable usually, so it is very hard to make very back drivable, free of movement. But our this special amplifier, I will explain it later. It is no time to explain detail. You'll find the individual file. So in this experiment, we apply each arm to take in this direction 100 Newton, 10 kilograms each arm, and the other way, he fixed the position with some low gain, and the other way, he fixed the arm with very low gain. Means that this side of arm is very flexible. We can place any place, and up and down this direction is quite visible, but not very visible. And pull down direction, each arm draws about 100 Newton. And what happened was that if you push arm this way, if this arm is not enough, then your leg will be lifted like this way. So this arm must be strong to move his body forward. And during that, this one keep pulling about 100 Newton, and this one must be flexible. So if you do this motion continuously, eventually it will drop.
Do you have the video back there? Okay, can you play it, please?
So that is very, very unique thing that we can achieve with that kind of thing. So it looks very simple, but this kind of jump motion is. We can skip this part and I'll show you later.
Okay. Okay, we are going to skip the video.
Yeah. So I skipped it. Sorry. And the drilling process, we have a first sensor here. Firstly, the operator indicate this one is the drill. We have to make kind of ROI, visual interest. Then LiDAR will pick the right one and it gives right direction and position and everything. Then robot will take that one, and the remaining thing is all automatic. And it will approach to the wall. And one more thing, operator indicate this one is a target. There are two ways. We can indicate point and diameter, or peripheral of circle, or we can put arbitrary point to make it in straight lines. So we have three options. So in this case, we choose the second option. The dark, the black circle, we put 3 points, and it equalizes the circle, and it moves in its peripheral with the 5 centimeters margin. And during the approach, we use photo sensor, so it touches the wall, it stops and keeps about 20 newtons of compressive force, and then make the circle. When you saw the actual things, you saw that the circle is very perfect. Means that our robot is very, very rigid and strong. We did the same experiment with the low down position and standing position. Actually, we complete all the mission with walking and rolling. We choose rolling for safety reasons. If we got very good point in first day with rolling, I would try to everything in walking. That was our plan. But in first day, we lost some points on drilling, and we got some trouble to show you actually walking.
We're going to questions now. I think it's the most effective thing to do. So why don't you line up the questions? We have around 8 minutes. We'll stretch that to 10, and let's get some questions. We'll give up on the presentation.
Yeah. I already presented most important things.
Excellent. First question.
Yeah. Thanks very much for your talk. One night in the garage, actually, when I was walking around, your robot followed me and picked up my phone, and stole my phone from my hand immediately, and grasped it and without cracking it. Can you explain me how you did it?
Actually, I didn't see what happened. We have the so-called manual control systems. So manual control, we scan LiDAR and they got a 3D image, and everything is manipulated in virtual space. So our arm and hands are moving. So I think that one of my operator tried that one. I thought, someone said when in second day, the Hubo robot walk around in the center of the floor, and some of you asked us that usually can you walk without safety gear? So because we put out the safety gear and just walk around. So my answer was yes. Since 1 month we removed safety gear, and because we usually put safety gear, at last if we remove that one, that operator cannot touch the key because it's too scary. So to make my students more brave and more experienced, so I asked them remove safety gear. It means that we have to confident 2 ways. Firstly, we must be very confident with hardware. Or little cables and sensors, one component missing, then we will get some catastrophic results. And software, if we get some balance or the stabilization and all the working algorithm is not quite confident, we cannot do that. So to make all the developers be confident, I asked them to remove the safety gear, and also we did all the experiment outside. In 2 weeks before leaving for the next phase, I asked to my institute to have big the parking lots, these are all parking lots, and we constructed all the same construction with very rough ground. It was very the parking lot was very old, so surface was very roughy, and also some inclination is this is not very good condition. So I told my students that we have to survive on that conditions. And also, in 1.5 years ago in Florida, we struggled a lot with the sunlight and wind. So we did the experiment in very heavy sunlight in the morning, during the noontime, evening time, and even they say tomorrow we'll have kind of gust and storm. So we expect very strong wind. So on that night, on that day, we took out the robot and all the tanks fly. On that condition, we climb up the stairs. So without the safety gear, of course. So that kind of thing is. So I think that this kind of mission, the balance is very important. If you have very strong robot, but few autonomy will fail, or the very flexible and the autonomy is good, everything is good, but platform itself is too flexible, you will fail. So good balance, rigidity and firmware, communication inside the networking, and level of autonomy and level of human intervention. All those kind of things must be very, very well balanced. So that is the most important part, and the intensive practice.
Next question, over here.
We are one of the Atlas teams, so we only have 1 robot. And at the end of the competition, a few months before the competition, the robot becomes a rare resource. So we use a lot of simulation to design and test our things. How much simulation are you using in your teams, and how does that help you?
Yes, that's a very interesting question. We have our own manufacturing facilities, and for us, hardware first, simulation last. Okay, that is very funny because developing software speed and making real robot speed is faster. So all my students doesn't like to play with the simulation. They want to have real robot and do the experiment. So we built actually 4 same identical Hubo at the same time. And once student tried to experiment with the real robot, they never want to do simulation with the simulator. So there are 2 things, the pro and cons. And pro is that we are dealing with real one, so this one is the final result. That's good. The con is that when you deal playing with the hardware, 80% time is maintenance of hardware. So the actual experiment time is very low, small. So when you are doing simulation, you can do experiment very many times and very effectively. But at last, if you put in real robots, then you got real trouble. So it's balanced, still balanced. So we made our own gazebo and own software platform also. So we try to make balance. So something, for example, driving type things, we use the simulation, and walking and actual mission, we do experiment.
Thank you. Over there. Next question.
Joanne Pransky, Industrial Robot Journal and World's First Robotic Psychiatrist. Dr. O, could you please describe the patents that Kaist or Rainbow Company goes through, or that you've accumulated or licensed on Hubo Plus 2?
Yes.
2 Plus.
Yeah. When my institutes allow me to operate the enterprise name Rainbow, we have protection. So 20% of the staff whole must be, the Kaist has 20%, and they allow us 80% for us. And then instead, the Kaist allows me to use any kinds of IP related from Hubo. So that was the rule. And frankly say that we do not have many IPs for Hubo. The reason is that because we were too busy to work, so there's no time to make different documentations.
Sorry, I apologise for the very prosaic nature of my question, but I just wondered how much it cost, and if you've got a sense of how that compares with the other teams.
Yes. If you are asking me the manufacturing cost, hard to say because we worked so hard. But just simply say that in Rainbow Company, we did deliver 15 Hubo to original small one Hubo. The price then $400,000 US, and we can estimate the price of if I sell this one, and I actually plan to deliver to anywhere. This one, the range would be in between $500,000 to $1 million, I guess. No more than that.
I think we actually only have time, I'm looking here, for one more question. So is there one more question? We need a person to go to a microphone.
Thank you for this, Sinjun from Twitter. And I think we have seen most of your doing, but we haven't seen your robot clearing the debris while walking. So have you prepared anything for that test while that robot walk forward?
Yes. Actually, a debris mission was clearing, not bulldozing. So we are very much good at removing debris missions. So if the mission was clearing all the parts with hands, then we do it because we practice a lot, and we expected that this mission must be much more difficult. So you have to put kind of bar not to get through. So you have to do very low. So we practice very low bar and something picking from down, and for a small one, we prepared a lot to remove debris with the hand, but we don't need to do that because just bulldoze everything. and also, we place a lot to negotiate with the rough terrain. We make very difficult, most difficult combination, the third stage. And to do that, we need to have very extensive simulation to get the right print. And to do that, the Hubo, we have very special working algorithm to stretch up to 55 centimeters with the 25 height. So we rotate the trunk, and sometimes we use toe kicks, and all the combination, so we could survive on very stiff and inclined terrain. So I'm people pity that we cannot present that kind of beautiful walking and the challenge.
I made
The problem, it was too easy.
We're running just around 15 minutes late, so let's